Welcome to TP's Chemistry Cuts Level 2 Quantitative Chemistry. In this clip we will be covering two SLOs. The first one is define and distinguish between empirical and molecular formulae, and the second we're going to interpret chemical equations in terms of particle and mole ratios.
Right then, so we're going to start a new topic, and that topic I put up on the board. It's C2.1 on the chemistry matrix, AS91161, and it's carrying out quantitative analysis. Right, so let's start looking at what we mean by quantitative analysis. Okay, so that's what's going to be the whole point of this lesson. What do we mean by it, and how does it work? So let's start with some very fundamental background that leads into it. I'm going to start by looking at equations, okay, and more particularly, this is chemical equations, formula that we use in them. Okay, there are two types of formula, and it's really important. First of all, you can distinguish between those formula, and secondly, what those formula mean in terms of an equation. Because if you don't understand that, then what we do that follows makes no sense at all. Okay? So let's have a look at the two types of equations. We start off with the simplest form, which applies to all substances. Okay, and that's an empirical formula. Okay, plural formulae. And the word empirical, one of those fancy words that people think, oh, that's complicated. In fact, it means it's simple. It's based on experimental observations. That's what it means. Okay? And what an empirical formula does is it tells you the basic makeup of a particle. So the simplest way of representing the makeup of a particle is to give you the ratio of elements within that particle. Okay, so that's what it does, and these are derived from experimental measurements, so that's why it's called empirical. So it's the simplest ratio of elements in one particle of a substance. Okay. Now the important word there is the word particle. Now, this refers to particles, and I just want to spend a few minutes going through what I mean by a particle. Okay, so you've got this right. We've just covered this in structure and bonding topic that we've just finished, and I have to say that particular part of the course you were pretty sucky at, most of it. Okay, so I probably need to go through this again. So this is all based on the premise that all matter is made up of a building block. Just like a wall, a brick wall is made up of a brick, all matter is much the same, a building block. So it's a repeating unit that goes on again and again and again. Okay? And so we're going to deal in terms of that building block all the time. Now, depending on what type of substance, as we've just found out in the last topic, the type of particle changes from substance to substance depending on what's in there, what type of elements. And this is something you really got to get sorted out. Okay? So the makeup of a particle, or what a particle is, depends upon the formula. Okay, we're going to look at that in a minute. We only really need to consider two types of particle now. Okay, these are ions. Okay, and we can pick that up if the formula that we're dealing with for a particular substance has a mixture of metals and non-metals. And a typical example would be something like calcium carbonate. Okay, calcium's a metal, the carbon and oxygen, both non-metals, so that's made up of ions. Okay, and that's one particle unit. that formula there corresponds to 1 particle unit. That's the building block that builds up, repeating this again and again, builds up a block of marble or chalk, okay, which is what calcium carbonate is. Now, if we've got only non-metals, then what we're dealing with is molecules, okay? So an example would be methane. Nice simple one where you've got carbon and hydrogen, but it's not confined only to organic compounds like that. We could have something like hydrazine, for example, or something else, so long as it's just made up of non-metals. Okay. Now this second type of particle presents us with a problem, in that when we're dealing with an empirical formula, it doesn't necessarily tell us the makeup of a molecule. It's just giving you the simplest ratio of elements in a substance. Okay? And so it's better for us. Our particle is made up, in that case, when we don't have the simplest ratio, is made up of more than the simplest ratio. So the formula isn't telling us what the building block is. And so we need a different type of formula, and that's a molecular formula. Okay? Now this will make more sense when we come to look at an example of a chemical equation. So a molecular formula makes allowance for the fact that an empirical formula may not, on occasion, tell you how many atoms there are in one particle, a molecule. Okay? So this is the number of each type of element in a molecule. E.g., okay, C2H6, and that's ethane. And this means that the molecule has 2 C atoms and 6 H atoms. Okay. Now if we go, or stay with ethane for a second, if its molecular formula is C2H6, what's its empirical formula? CH3. Okay, so CH3. What does that mean? If the empirical formula is CH3, what does that actually mean? It's really important you can say this to yourselves. Yeah, so it's telling you, if it's CH3, it's telling you for each single carbon atom, there are 3 hydrogen atoms. And that's true, but it's not useful to us. What we need is the number of each type of element in one particle. Okay? And in this case, in the case of a molecule, it's not giving us the right answer. We need a molecular formula, because that's what we want to do with these formulas, to see how many of each particle reacts together when we do a chemical reaction. Okay? So that's our starting point. Okay? Now what I haven't done on here is to say you, or written up, what we mean by an empirical formula. So why don't I use the example I've just done for ethane and put the what the empirical formula for ethane is and what it means. Okay, so empirical formula for ethane is CH3. Okay, so long as I actually highlight that, and then highlight the thing down here where I've given the molecular formula, and then you can compare the two. which are different for the same substance, and you can see the different meanings. Now, I should emphasise here that the empirical formula and the molecular formula aren't necessarily always different. Anybody give an example of a compound where they're the same? H2O, okay? It's the empirical formula because it's the simplest ratio. It also happens to be the same number or the same ratio, the simplest ratio for that substance. Okay? So they're not always different. But it's something you need to keep in mind that when you're dealing with ionic substances, you can only ever deal with an empirical formula. When you're dealing with molecular substances, you should be using the molecular formula. Okay? Now, the reason for this is because in chemistry, of course, when we come to represent reactions, we do so using a chemical equation. And this is the rub. This is the important thing. The actual chemical equation is telling you how many of each type of particle are reacting together and how many of each type of particle are actually being formed as products. And that's what you've got to remember. So the very first thing you do with the chemical equation is to identify the type of particle you're dealing with, and then you know what type of formula you're dealing with, whether it's an empirical or a molecular. Does that make sense? Okay. So I'm going to take a simple reaction, okay, a very simple reaction, and we'll use perhaps the formation of water from its elements. So if we take two H2s, and let's do this at level 2, so we put in all the information we've got, and we take an oxygen, and that means we form two water. Okay. Now, armed with this, there are two ways armed with this, there is a simple way in which we can actually interpret this equation. What we're doing is we're taking two particles of hydrogen, whatever those are, and we're reacting it with one particle of oxygen, and we're making two particles of water. Okay? And that's a very important point to make, because it's giving us the ratio of each of the species in that reaction. In other words, I need two of these for one of those to form two of those. Yeah? So it's all in terms of particles. What type of particles are we dealing with here? Molecules. Because, as it says up here, that's just made up of non-metals. It's two non-metals. It's the same non-metal joining by a covalent bond, but it's only made up of non-metals. That's a molecule. So I'm taking two molecules of hydrogen. What about this? It's a molecule, again. So one molecule of oxygen. So I'm taking two molecules of that, two particles, and I'm reacting with one particle of that to give two particles of that, and those particles are molecules again. Okay? And Paige is falling asleep. Come on! Is it because it's too hot, or is it because I'm boring, or is it because we're both?
I'm just tired.
Now, so that's where we are. So why should we write that up?
Oh, body. It's amazing. My equations are like, look at my book. I can see like
So that's our first step. Now we've got our information about the type of formula we're dealing with. I've got two molecules of H2. Yep. Say plus one molecule of O2 gives two molecules of water. And we've got that because we're using the information from the formula. So that's the first thing that the formula will always tell you, what type of particle you're dealing with. So that's basically the level you would be at the end of perhaps level 1. Okay? What we want to do now is to take you up to level 2. And we've already touched on this when we looked at quantitative calculations for energy. But we're going to go through it again. The problem we have with that is it's not possible to take two molecules of one thing and one molecule of another and carry out a reaction, and neither would it be meaningful. Okay, so we have to have some way of scaling this up so we can carry out reactions like this in the laboratory. And the reason we want to do that is because if we're going to do a reaction between these two things, it would be nice to know exactly how much of each we need if we want to make a certain quantity of the product. And that's what quantitative chemistry is all about. It's about putting quantities to things, because that's what we need to do in reality, in industry. If you're making something, you need to know how much of the starting materials you're going to need to react together to make it. Okay, so how do we do that? Well, it's simple. As you've already seen, we need a scaling factor. Okay, so let's have a look at atomic structure to see how that scaling factor comes about. Okay, so let's have a look at how we scale up from individual molecules to usable quantities in the classroom. Okay, so if we look at a single carbon atom, okay, we can, from your year 11 information that you've learned, represent its structure in a very simple way. Okay, and I'm going to do that now. So if I write it like this, what does that actually mean? What's this number at the top?
12.
12. Yeah, okay, it's 12. What's that representing?
Mass number.
The mass number, okay? So that's the mass number.
There you go. There we go.
And this one here, atomic number. Right, before we go on, let's just remind ourselves of why each of these is important. What's the important thing about the atomic number? What's that tell us?
How many protons are in it?
How many protons are, and why is that so crucial? Why is it we have to know
The
that?
number of protons makes that one.
Exactly right, thanks. So this number is telling us that in fact we're dealing with carbon. In fact there's 6 protons. If you were to change that number, we're dealing with another element. That's the way it works, okay? What about this number? What's it telling you?
Protons. Neutrons.
The total number of protons plus neutrons, which is telling you what? What is it? It's basically the mass, because as we know, most of the mass is centred in the nucleus. Yeah? Right. So, if one carbon atom contains 6 protons and 6 neutrons, it's telling us it's got a mass of 12 atomic mass units. Okay, so and this is not something you usually come across because we don't use them. We can't just take one atom and weigh it. It's not possible. What we can do though is we can scale it up. So if we have a certain number and they're all the same mass, then we know that it will have a certain weight or mass. Okay? And so if we take what we call Avogadro's number, and that's equal to 6 times 10 to the 23. So in other words, approximately that, it's 6 with 23 zeros after it. Was it 22? Yeah, so it's 23 zeros. Yeah? Which is a pretty big number, and it's not something that we want to be dealing with all the time when we're actually quoting this. So we call that a mole.
Mole. Oh, really nice.
Okay? I'm going through this for the benefit of the camera. Thanks for sort of raining on my parade, Chris Simmons. You are now going to be a legend on YouTube, you know that. Hey, My name's Chris Simmons and I'm on YouTube. Okay. Now, the reason we take this bizarre number, okay, is it takes the mass number in AMUs and converts it to a mass number in grams. Okay? So, C12, okay, is equal to 12 AMU. So if I take one C12 atom, it basically is 12 atomic mass units, in other words 6 protons, 6 neutrons. If I take a mole of it, however, 1 mole of C12 is equal to 12.0 grams. Now don't worry about the number of figures for the moment, we'll come to significant figures later. So in other words, I've dealt with something fairly esoteric, look it up people, and I've got something that we use fairly commonly, okay, and that's a mass in grams. And if I weigh out 12 grams of carbon-12 isotope, I know I've got exactly 6 times 10 to the 23 of those. Okay? So it's nice and handleable quantities, and we know how many atoms we're dealing with. Now there is an issue. Okay? Houston, we have a problem in that we have not allowed for the fact that some elements on Earth exist in more than one form. In other words, isotopes. Now, carbon is not one of those. The vast majority of carbon atoms on Earth are this isotope. So, if you were to take a mole of carbon atoms, it would be very close to 12 grams. But if you take something like chlorine, a mole of chlorine atoms on Earth does not have a mass of 35 grams, which would be nice and convenient. It's 35.5. And it doesn't mean that we've got half a neutron there in each atom. It's because we have a percentage of a fixed percentage of 2 or more different isotopes. So, can somebody remind me? Chris seems to like being on YouTube, so Chris can remind me, what do we mean by an isotope, Chris?
The mass number changes.
But yes, so in other words, we've got the same type of element, in other words, the same atomic number, but the mass number varies, okay? And so let's look at isotopes. And as I've said, a classic example is chlorine. Okay, so we've got 2 isotopes. No, I've done it wrong. That should be 37. I was right first time. Okay, so we've got 2 isotopes, chlorine 35 and chlorine 37. We know they're both chlorine because they've both got an atomic number of 17. But the difference is that chlorine 37 has an extra 2 neutrons, so it's got a higher mass. And on Earth, if you take a sample anywhere on Earth, statistically you'll find that 75% of the atoms will be that, and 25% will be that. So what we do to work out the mass of 1 mole is to take the weighted average of those 2 isotopes. So in fact 75% of 1 mole is that mass and 25% is that mass. So weighted average equals 75 over 100 times 35. Okay, so that's due to this chlorine 35 isotope, and then we add the 25 over 100 times 37, and that's due to the other isotope, and you'll see that it's 35.45. Okay, so I'll put that in. That's Okay. So what I've done here, or quoted here, if I put G there, it's the mass of 1 mole of chlorine atoms that allows for the fact I've got 2 isotopes, and that's what you would find in their natural abundance on Earth. Okay? And this is an example of an atomic mass. Okay, so this is what we call the atomic mass. So I'm going to put that there. Atomic mass. And it's the mass of 1 mole of an element allowing for natural abundance of isotopes. Okay. Now we will actually do some examples in a minute because we're going to use these. Okay. So that there is the first thing that I wanted to get to in this lesson. What we mean by an atomic mass. Because we're going to use atomic masses throughout the rest of this topic, and it's really important you know what we're referring to. Okay? So it's just the mass of 1 mole of, at the moment, an atom. Okay? Now let's go back to our original equation that we dealt with. Okay? So the equation we dealt with was 2H2G plus O2G going to 2H2LO liquid. Okay? So this means now that rather than dealing with molecules, we can deal with moles. We can scale it up, people. Scale it up. Okay? So, 2 mole let's keep it all on one line. So if you look at that equation,
So how does that work? Because doesn't 1 mole like a certain number of particles? In the same
what does this say?
2. Yeah, but I thought a molecule was like the exact number of particles.
But the number in front is telling you how many particles are reacting, not how much is in those particles, and that's reacting. You see that? So that's what that 2 does. The 2 tells you what the particle's made up of. This is telling you how many. Is that clear? So the number, and maybe I should write that down, so that's a good point. Okay? The number in front of each of these species tells you how many particles are reacting. Is that clear?
So the number afterwards, that subscripted, that tells you what.
Whereas the subscripted numbers are telling you exactly that. Yes, the subscripted is how much of each type of element are in the substance. This number in front is telling you how many particles are reacting. Okay, so why don't we put that in? Should we do it in a different colour, just to emphasise the point? Okay, so we'll do it in blue. So, okay, so the important thing there is it's how many particles you're dealing with. Okay, so that's the number in front. So the fact we've got a 2 in front of H2 here is telling you we're using 2 of these particles. This number here is telling you that that particle itself is made up of 2 hydrogen atoms. Right? No? Yes? Hello? I think everybody's gone home. They're so bored. Right. Okay. Now, the next step, if everybody's happy with this, so you can interpret what it means, is how do we know when we've got 2 moles of this? How do I know when I've got 1 mole of that? And what happens if I don't want to actually use 2 moles? I actually want to use 0.65 of a mole, just off the top of my head. How do I know I've got that? And this is where we start talking about molar masses. Okay, so what we need to do is to look at what each particle is made up of and use the number of each type of element and sum up their atomic masses, and that will give us what we call a molar mass. And a molar mass is a mass of a mole of the particles we're dealing with. So, and it's really important you understand this. If we're looking at this particular species in this reaction, the first thing is you ignore the number up here. That number is not part of this calculation. It's one of the mistakes that a lot of people constantly make. They double dip, because you're going to use that number later. What we're interested in is the mass of one of those particles, or the mass of 1 mole of those particles to start with. Okay? Because that's what we're going to find out, because that's what the molar mass defines it as, 1 mole, not 2. Okay? So, let's write down molar mass. Okay. So that's what the molar mass is. It's the mass of 1 mole of particles for a given substance. Right. Okay, so let's have a look at an example, because that's what we're going to need. We're not going to look at individual atoms anymore, we're going to look at particles. Because reactions are between particles, not individual atoms. Okay, so, e.g., water is H2O, so this is equal to 2 times H plus 1 times O. 2 times the atomic mass of hydrogen, which is very conveniently 1.00, plus 1 times the atomic mass of oxygen, which again is very conveniently 16.0, and that gives us a molar mass of 18.0 grams per mole. That's the unit. That tells us that for each mole of water, you have a mass of 18 grams. Yeah. Yes, we'll talk about significant figures later. Okay, you'll notice I'm quoting everything with 3 numbers in it all the time, and there's a good reason for that. But we'll come to it when we're ready to come to it. Okay. Can I rub this side off? Hey, we keep cooking on gas now, people. So what this means, or the way we represent this, is to use the letter capital M. So for water, we would use capital M, and then we put H2O equals 18.0 grams per mole. And this means 1 mole of water molecules